So in order to have a good understanding of induced seismicity, you really need to have a good understanding of geomechanics. You need to understand how the earth forms, how the stresses are organized in the earth, those sorts of things. So Brian already gave a brief introduction of just sort of who I am. And I actually did my undergrad with Brian a million years ago. And then I went to Stanford with Mark Zoback. And as Brian said, Mark Zoback is, I'd call him a reservoir geomechanist rather than an induced seismicity guy. But he is big name in the field. And then I came back to the University of Utah where I'm doing my postdoc / research scientist position with Professor McPherson, sort of back and forth. And then so to give an outline of today's lecture, we're going to start with an introduction to stresses. We're going to make sure everyone has a good solid grasp of what a stress is. And then we'll talk about the stress tensor. This is an important mathematical quantity that allows us to describe systems. And then we'll talk about principal stresses, which is a certain way of orienting the stress tensor so that you can understand different phenomenon in the earth. We'll then go to strain, which is the result of stress. So you apply a stress, you then get a strain. And then we'll talk about the elastic moduli, which are measures of a physical system. So a rock, a good example of that is a rock has elastic moduli. It's like the density of the rock. It's just a property of the rock. So let's start with the introduction to stresses. So I'm going to posit a question. What is a stress? Does anyone know what a mechanical stress is? Is anyone willing to go out on a limb?
I would say it's force in a static system per area.
Yeah, force per area. That's a good way to think about it for sure. Anyone else? Does it vary in a physical system? Is it a uniform quantity or does it have heterogeneity? Yeah, it has heterogeneity for sure. And so these are all correct answers. And so like you said, it's force per area. So that is essentially what the units of a stress are. And so if you think about that in terms of system international or imperial units, that's pascals versus PSI, pound per square inch. And there's a really easy conversion between the two, which is that 1 megapascal is roughly equal to 145 PSI, or if you're doing back of the envelope calculations, that's basically the same as 150 PSI. Makes it very easy to do calculations. And to give you a sense of like what these quantities, the magnitude of these quantities in here, at a depth of about 3 kilometers, you have stresses on the order of 3,000, 6,000 PSI, which would be about, anyone want to do the math for me? 6,000 divided by 1.5 is what, 300 MPa? All right.
Be
4,500 MPa, 45 MPa.
All right.
Okay, so how does a stress differ from pressure? So we all know that pressure is also a force over an area. And so what does it mean for a stress versus a pressure? Does anyone already understand that or have a grasp of it?
Yeah, I would assume that pressure is unidirectional, right?
That's right. So keep going.
Whereas stress is a tensor.
Exactly. Yeah, so there's a directionality to a stress. So a pressure is a uniform quantity that is essentially integrated over a fluid, usually. Yes.
So unidirectional implies one direction.
No, it was the wrong word. It was the wrong word, but it was the correct. It was the correct thought. Wrong word.
Isotropic, right?
Yes, isotropic.
Yeah.
So stresses act with a direction. There's a direction associated to the stress, while pressure just acts isotropically. And so we can think of stresses even further, get a little more into the detail of it by looking at what happens at a point. So if you imagine you have a patch of some surface, and you have a force acting on that patch, and we'll call this F. Then that force acting on the patch divided by the area of the patch is the stress, yes? No, it's actually not. So the stress is actually at a point where you take the limit of the force divided by the area as the area approaches zero. And what that's called is the traction. So that's the traction right here. And this, so say instead of having the force coming completely orthogonal, we have the force coming at an angle. The force is coming at an angle, and then the traction then is going to have a direction associated with that direction of the force. And so that's, oh, yeah.
If I take the stress and dot it with a vector, that's an attraction. So
Oh,
that's traction in a certain
yeah,
direction.
yes. So let me go to the next thing. So this is essentially a matrix multiplication. It's not a dot product because it's three-dimensional. Both the normal vector and the force vector or stress vector or tensor are three-dimensional. So you actually do multiplication, and this is called Cauchy's formula, which is essentially saying that these tractions, or at least the components, the XYZ components of the tractions, are essentially a function of that force acting on that vector, the normal vector. So the point I wanted to make with this is that if we reduce the size of this patch and reduce the size of this patch and reduce the size of this patch to a point, that's what you should think about with the stress. The stress is a point in the solid medium that corresponds to all of the other stresses and forces acting on it, and there's a directionality to this. And we'll get into that in a moment about the directionality of that point. So that's what you should think of when you think of a stress. It's a point in the physical medium, and that point corresponds to stresses and forces in the medium.
So in your notation, you use the bold to represent a vector.
I'm inconsistent. I'm not a mathematician. I'm inconsistent about that. Usually I use bold is a vector in this case. Yeah. So these are components. This is component of the stress tensor. This is a component of a vector, component of a vector. I didn't do the bold. I'm not a mathematician. I apologize.
Yeah, that's perfect. That's perfect. And that's a good way to do it.
Okay. And now just to give you a sense of what this looks like. So you have kind of like a theoretical understanding, like it's a point in a solid medium, forces are acting on it, there's a directionality to it. And so now we're going to look at, this is from a paper that I found online, and this is a pin joint. It's a joint that's used in aerospace engineering. And what they're looking at is this portion of it. I'll use my pointer on the computer. This portion of it right here, they're looking at the stresses resolved on it for a certain amount of torque. So you can imagine you take that pin joint and you apply 200 Newton meters of torque. And what are the stresses that then get applied to different components of that pin joint? And so here you can see a numerical model of these stresses. And from that numerical model of these stresses, you see that there's certain places where the stress concentrates. There are other places where the stress is pretty much unperturbed. And so I just wanted to show this to give you a sense of, this is what it looks like to model stresses. This is what you can imagine stresses looking like in a solid medium. Do we all feel okay with sort of what is a stress? It's kind of like yes.
Just one quick question.
Uh-huh.
In the past, I've characterized stress as like a body force.
I don't think that's very fair, because
Or
usually
is
body force,
pressure more body force?
What's a body force?
I would say pressures, a body force is a force that acts across an entire medium.
So pressure is more.
Pressure is more of a body force, gravity is.
That's what I was thinking, was pressure is the body force and stress is a surface
Uh-huh,
applied to it.
Yeah,
Because there's a normal and a tangential component.
exactly, yeah,
Yeah.
there's directionality, there's directionality. Yeah, so I don't think it's quite fair to say that stress is a body
I
force.
mean, pressure, that's what I meant, to say was pressure.
Pressure is a body force, or can, I'd have to think about that, but gravity is what I always think of for body forces. And also when you're talking about plate tectonics, like the convergence of two plates, you consider the collision body forces. Yeah.
Well, is there a system where material will react in a noticeable way directly to how much stress there is at a point? I know I've
yeah.
seen that with polarization, but
yeah.
what's another good example of something?
So if you have a stress concentration, the material can break. There's a uniaxial compressive strength of the material. And if you exceed the uniaxial compressive strength of the material, aka the stress is too high at the point, the material shatters.
And how much the material stretches or acts is dependent on?
Well, okay, so I think you're a little ahead of where we are right now in the lecture. But when we get there, we'll revisit this thought, because it's very important to understand that, like, it's an entire system of deformation that occurs before the failure of the material, and it is very much related on stress and the material's response to stress.
Knowing what Kevin's covering today, I'd say if you have a question for clarification, ask him. But then stuff like, oh, what's another example, to go into it for further discussion, let's save towards the end.
Yeah. No, absolutely. And I mean, yeah, I appreciate questions.
He loves questions.
It's easier to keep.
Yeah.
Okay, so let me ask that question again, though. Does everyone feel okay with the concept of what a stress is? Does everyone feel like that's kind of like it makes a little bit of sense? Yeah, okay. Okay, so we're going to move on to the next part of this talk, which is the stress tensor. So this is a mathematical way of understanding the stress state at that point, whatever that point is. And first, we're gonna take the point and we're gonna say, instead of just some nebulous singularity in space-time, we're gonna instead of think of it as an infinitesimal cube, or in this case square, because it's two dimensions. And so this infinitesimal square has a shear stress and a normal stress on each side of it. And you can also imagine that you could do this in non-Cartesian coordinates. You don't have to do a square. You could do a circle or a cylinder for spherical or cylindrical coordinates. And it's just as valid. The mathematics are different. They're more complicated, but it's just as valid to do this with a spherical or cylindrical coordinate system. And oftentimes in geophysics, we do use cylindrical coordinate systems because of well bores. The trajectory of a well, we like to use cylindrical coordinates because it's easier to describe the system that way.
And remember, we derived the groundwater flow equation using infinitesimal cube and mass balance in that infinitesimal cube. And then we discussed the conductivity tensor, which is a great analog for this.
Absolutely.
The conductivity is the analog to this, not this is the analog to that.
Absolutely. Yeah. Okay. And so this is this. Hold on, let me do this better. Voila! This is the stress tensor. So S sub ij indicates I is the row and J is the column. It's just initial notation. And so in this tensor, you have values that correspond to this system. You have S22, which is S22 here, and that is the normal stress acting on this surface and that surface. And you have S11, S21, S12, S11, S12. I forget where I was. But anyway, you have all of the stresses that are resolved on the cube applied to in this tensor. And so you can see immediately that the 1, 1 and the 2, 2. So if the I and the J are equal, that means that you're talking about a normal stress. Talking about a stress acting on one side of this infinitesimal square. if you see that the I and the J are different, 1, 2, 2, 1, you see that you're talking about one of the shear stresses. This is stress acting across the surface, and that is corresponding to the off-diagonal terms. So what would it mean for the off-diagonal terms to be equal to the diagonal terms? Let me rephrase that. All four terms are exactly the same. What would that mean? Think about the infinitesimal cube or square.
It would be zero stress.
Zero stress. I like the thought. There's sort of zero relative stress, right? Yeah.
So to make sure I understand the off diagonal terms, and so if you just have a regular pressure, that would just be in a diagonal identity. Some pressure would be a stress tensor with an identity matrix times some constant. Is that right?
The pressure is not a tensor. There's no tensor.
If you were to replace it with a tensor, it would be an identity. I mean, generally speaking, when you have an identity, you can just replace that with a single number.
But so if you have an identity, and yeah, I mean, yes. So an identity would be in geomechanics we term that a hydrostatic system. We consider that a hydrostatic system, and that would definitely be kind of a proxy of pressure.
And so the off diagonals are like torque. Is that right?
Shear is what we usually say, but
if you apply, okay, good. And or is it symmetric, or is S21 always the same as S1?
I'm getting there.
Okay.
You're asking the next slide each time. You're teeing him up, so great.
So if all of these terms are equal, it's isotropic. All of the stresses in the square are the same. And so that's an isotropic stress state. And if there's any kind of difference between these terms, it's an anisotropic stress state, which means that the stresses on the cube or square are different. There's a different stress this way than this way. There's a different shear stress this way and this way. That's the concept of anisotropy, at least in the stress tensor. There are other ways to think about it. And so, as Brian was saying, the S12 and the S21 terms, these are the off-diagonal terms, and they correspond to the shear stresses. These two stresses, what if they're different? What would the result be if they're different? Yeah, you'd have torque. That's what you were getting at. If they're different, you apply a torque to the system. Luckily in geomechanics, in the Earth, there's no torque. The Earth doesn't, I mean, over geologic times, yeah, things rotate for sure. But like in terms of the static state of the Earth, there's really no torque. And so we don't ever consider the off-diagonal terms, that S12 and that S21, to be different. So and then that the term you used is symmetric. That is the correct term. It's a symmetric matrix or tensor. Yeah.
So you're saying if it's asymmetric, then it would start to rotate?
Well, there would be torque, right? Because it's not a matter of like what the actual system will do. It's a matter of the stresses resolved in the system.
So I don't understand. I don't understand. So you call that shear stress.
Uh-huh.
And when you have torque, so if you have a shear going.
People will need to get up to strain, and then the torque will make.
Sure. Yeah.
How about the unequal in normal stress?
Unequal normal stresses, that is totally okay. That is totally okay. You can imagine you can push harder this way than this way. They're totally okay. We deal with that all the time. And we'll talk much more about that later. Yeah. Okay, so, and this slide is just demonstrating that the same thing exists in 3 dimensions as well as 2 dimensions. And it's none of the concepts are different. You know, we now have 3 normal stresses And this is usually the stress tensor that we use because the universe is three-dimensional. And so you have 3 normal stresses and now 6 shear stresses. But the thing is, like Brian said, these 3 shear stresses are equal to those 3 shear stresses, or else a torque would be applied. And in the earth, we just don't see that. It doesn't really exist. Okay, so now we're going to get into the concept of rotating a stress tensor. So we've probably all seen a rotation matrix before, used it maybe in high school or something. And what it does is it mathematically translates or rotates an image from one orientation to another. You'll see why this is important in a moment, but for now we're just going to focus on the rotation matrix. And this is a matrix, not a tensor, because there's no directionality. There are no dimensions associated with it.
While you were erasing, I want to say that I attended high school in Oklahoma, and we were not rotating matrices or tensors in high school.
Sorry.
We did addition and subtraction. We were doing more.
Apologies. So we're going to take a system. All right, so we're going to take a system. And we're going to rotate 1 point. So we have 1 point out here in space, and we want to rotate it exactly around the origin. So we'll rotate it around a circle where the radius is the same at every location. And we'll rotate it from here, which is going to be x to y, or sorry, x comma y. And we'll rotate it here to x prime to y prime. And this value is the radius. And this value is also the radius. And we'll call this angle right here omega. Can you see? My head's in the way. I'm sorry, my head's in the way. So this value is omega, and this value is theta. Okay. And then so we're gonna sort of figure out, how do we get from point A to point B? How do we do this? So the first step is to represent the XY coordinates in terms of trigonometry. So we say that X is equal to, so we draw a right triangle here. So this is omega SOHCAHTOA. X is equal to R. Oops, I should put that on that place. R. So X is equal to R times the cosine of omega. And then we have Y is going to be equal to, obviously, the sine times omega, or the sine of omega, R times the sine of omega. Y equals R times the sine of omega. And so that's this point. And let's do the same thing with this point. And this is going to be X prime equals R times the cosine of theta plus omega. And this is going to be Y prime equals R times the sine of theta plus omega. And now let's make sure everyone's on board, right? This makes sense, because the angle from here to here is theta plus omega. So that's why we're doing the cosine and the sine of theta plus omega. Is everyone okay with the trig? Omar's okay, I like it. Okay, and now we're going to use trig identities to expand this expression. You remember that you have trigonometric identities that allow you to represent quantities in trigonometric functions in different ways. One of those identities allows us to do.
I know where you're going, man.
One of those identities allows us to do X prime equal to R cosine omega times cosine theta, and that's gonna be minus R sine omega times sine theta. And then let's finish out this before we go to y prime.
That's the double angle for, oh yeah.
I kind of skipped a step usually. Usually you don't put the R, you don't distribute the R immediately. I already distributed the R, so usually the R stays here and you represent this part.
Yeah.
That might have confused you.
That's good.
And so let's finish this out. So R cosine omega, we already know what R cosine omega is. It's just X. So this equals X times the cosine of theta minus, and R sine omega, well, that looks familiar. It's just Y. So this is Y times the sine of theta. Okay, so that's what X prime is. And now Y prime, in a very similar fashion, is going to be equal to R cosine omega times sine theta plus R sine omega times cosine of theta. And it's the same thing. We already know what R cosine omega is. That's just X. So this equals X times the sine of theta plus an R sine omega. R sine omega, that's Y. Y times cosine of theta. And so now what we can do is we can write these two expressions out a little more clearly. Allow me to maybe. Are you okay with this diagram? Does everyone feel comfortable with the diagram? Can I erase it? Yeah, okay. So I'll leave, maybe I'll just erase it. So now we have X prime. I'm just rewriting the exact same thing, just a little more neatly. X prime equals X cosine theta, X cosine theta. Is this marker legible enough?
It was looking good
It was,
before.
Yeah, it started to get good, but
All right, yeah. Let's do that again. So X. I don't know if that's much better.
This is bad.
So other X prime equals X cosine theta minus Y sine theta. And then Y prime equals X sine theta plus Y cosine theta. And that looks suspiciously like a system of linear equations. Just does it feel like linear equations to anyone else? And so
pretty darn linear.
and so this is just equal to the vector X prime, oops, that thing, Y prime equals, let me get this in the right order, equals cosine of theta sine of theta negative sine of theta and cosine of theta. And that is multiplied by your x's and your y's. So the original point, x and y. And so if you multiply X and Y, the original point, by this matrix, which is the rotation matrix, you get the new point. And so theta is the angle of rotation. Just a fun little derivation. Trust me, this is relevant.
Yeah, and if you multiply the matrix for theta and then multiply matrix for omega, you're back to those cosine theta is right? The double angle. If you multiply two different matrices with omega and theta, then you get cosine theta plus omega, cosine and sine.
I will
theta
take
plus
your
omega.
word for it.
You should.
Sounds good. Sounds good. We'll roll with it. Okay, so that's just deriving the rotation matrix in 2 dimensions. There's a 3-dimensional rotation matrix as well, which is much nastier. But in 2 dimensions, that is the rotation matrix. And so now we're going to think about what it means to rotate a tensor, right? Because we're not rotating the physical object, we're rotating the axes by which we're applying the directionality. And so you can see that what that means is you rotate that that infinitesimal unit cube or square, whichever the case may be, or sphere or cylinder, whichever the case may be. And so this is my joke. Everyone get ready. This is my joke. So what does it mean to actually rotate the tensor?
How do you,
Yeah, let's lead into this. So say that again.
how do you rotate this tensor?
Well, you rotate the tensor. Okay, sorry. And
How you don't look enthused. It's like over there. It's like a bad math joke.
bad matchup. Like this nerd.
I paid tuition for this.
Okay, so we have the 2 elements now to actually rotate a stress tensor rather than my joke. So we have our rotation matrix, which we derived just now. It was very fun. And then we have our stress tensor, which is a representation of the system. And you just multiply them together. It's just matrix multiplication. You just multiply them together and you get the new rotated stress tensor. And this has no bearing on the physical reality of the system. You can rotate the stress tensor all you want and never change what's actually happening to the system. It's just the mathematical way of describing those forces. And so now we're going to do a little example in MATLAB. So we have our rotation matrix, and we're going to rotate some stuff. We're going to take a square and we're going to rotate. Let's start by 180 degrees and see where we end up. So I need to drop out of PowerPoint.
The only one who loves MATLAB.
Sorry?
I'm not the only one in the planet who loves
MATLAB is such a crutch. It's so easy. It's just the easiest programming language.
I hate MATLAB. I think it's the worst programming language.
Okay, so I'm going to walk you through the. Let me blow this up for you guys. Let me maybe put there. And let's get this. How do I make this bigger? Can I just do? No, I can't. Okay, can you guys see that well enough? The code?
Yeah. It'd be nice for a little bigger, but
Yeah, I would like to.
Not
Get,
bad.
I would like to get it bigger, but I don't know how.
try control.
I tried Control Plus.
Yeah.
Yeah, it's not working. Maybe View. Huh. Well, okay. Well, I won't belabor the code then. Essentially, it's just this is the square. These are the points in the square, the vertices of the square, and then this is the rotation angle. This is the rotation matrix that we just saw, and this is the multiplication of the square and the rotation matrix. So when we do that, we get a square that's been rotated. Oh, I need to move this. We get a square that's been rotated by 180 degrees. And you can see the point that's directly at the origin, because that's the point around which we're rotating, is completely stationary. It doesn't move. And so let's have a little more fun with it. And instead of doing 180 degrees, let's just do it randomly. Let's just a random or rotation. So that looks like about, so obviously it's got all the, so mathematics is usually clockwise. Almost always mathematics is a clockwise language. And so when we see a rotation like this, it hasn't rotated like that, it's rotated like that. And so this is like 100 or 305 degrees or something. It's like 305 degrees of rotation. Let's do it again. Why not? So this is like 335, 350. Let's do it a couple more times. So then that's about, oh, that's almost exactly 90. Oh, 45. That's almost exactly 45. Kind of cool. And then let's do it one more time, just for fun. And up we got 300 something again. So that's what it's like to rotate in 2 dimensions. Let's take a look at what it looks like to rotate in 3 dimensions. The code is very, very, very similar. So instead of having a square, we now have a cube, and each vertice has 3 dimensions to it. So there's an X, Y, and Z associated with each vertex of the cube. And instead of rotating by a single rotation angle, you can now imagine that there are 3 degrees of freedom. You have the yaw, the pitch, and the roll. Let me get this right. So the yaw is this, the pitch is this, and the roll is this. So you have 3 angles that describe rotation in 3-dimensional space. And so we put angles in for those 3 angles. And the rotation matrix now is much more complicated, as you can see. I am not going to derive this one. That sounds terrible. But I was able to pull it off Wikipedia. So,
So if you have a pair of vectors, there's 3. If you have a single vector, there's 2, right? Because I mean, you need, since 2 dimensions, there's just 1. So you would say there'd be 2 for 3 dimensions, but if you have something with 2 vectors, then one of them's not the same.
I don't understand.
So a single vector only has theta phi its rotation.
I'll take your word for it.
But
I'm talking about a physical object in space has 3 degrees of freedom of rotation.
yeah, because it's defined with more than 1 vector.
Okay.
If you define a single vector, it has 2.
You know, it's not a question if you know the answer.
Well, I'm not sure because this rotation matrix has, I don't know. I'm just thinking that.
I appreciate your engagement. It's all good. So yeah, so now the rotation matrix is more complicated, significantly more complicated because we have 3 angles of freedom. Yeah, but the equation is just the same. You multiply those vertices of the cube by the rotation matrix, and using just a fixed value, we get some degree of rotation in 3 different angles, 3 different yaw pitches and rolls. And these angles correspond to that new red cube. And you can see again that the origin point, the point at the origin, does not move. It's because that's the point around which we're rotating. Let's now have a little more fun like we did with 2 dimensions. And now we have random rotations. We just randomly rotate this cube in 3-dimensional space. And so this is all suffice to say that mathematically we can describe rotations. And rotations are going to be very important in geomechanics, in the stress tensor of geomechanics. Okay, so let's get out of MATLAB. And I think
I think I know what was confusing.
And so I think we're about halfway through the class, if I'm not mistaken. So let's take a little break. Let's stretch our legs, get some water, relax a second. let's give it like, let's give it 4.
Paradigm for this, for my teaching. I've never given breaks. Now I have to. Now I must.
If you end on
Otherwise-
time, it might be too much too.
I won't tend to, we're probably, actually, it might be close. We're halfway through it at intermission. We'll see. Let's see what happens.
If I don't give them intermission from now, I'm gonna look like a putz.
Sorry, Brad.
I think what I was wondering about on that matrix is, that the 2D matrix doesn't have any eigen, vectors in the real numbers.
A 2-dimension never does. Is that true?
Yeah, because there's no angle that you can have rotated in 2D that's not gonna rotate, right?
Oh,
But in 3D, if you pick a vector, you can rotate it around that vector, and that matrix is its eigen.
yeah. I think of eigenvectors more less in terms of rotations and more in terms of what is it? It's what's the symbol for an eigenvector? Lambda?
Yeah, well, that's eigenvalue, and
Eigenvalue.
then you can just I don't know, just it's a B or something. I would do B.
Sure. So what is it? V equals lambda A, or no, it's lambda B equals.
VA is lambda A is what it is.
There it is. VA is lambda. Thank you. So VA equals lambda A. And so what we're doing is we're going from a vector multiplied by a matrix. Is that right? Should we matrix by a vector? It should be a lambda, right?
AV is, let's see.
Or sorry, AB, yeah. It should be AB.
It's the other A. I guess it should be AV because
AB. I
vector
agree.
goes
It should be AB. AV
is
equals
lambda B.
Lambda B, yeah, it's not A, it's B.
There we go.
There it is. That's the eigenvector.
Yeah.
So I don't usually think of that in terms of rotation. I think of it in terms of like axes in the matrix, so like bases essentially.
Okay. Well, I mean, if you think of rotation in terms of this way, there's a neat way to understand.
Sure, I trust.
The eigenvalues are always 1 in a rotation matrix.
Uh-huh.
And that's to represent the fact that if it's a rotation matrix, it doesn't lengthen the vector.
Uh-huh.
It just rotates it, right? It has the
That
same
makes
length.
sense. That makes sense. Yeah.
The change of length in the rotation would be, or the operation would be the lambda.
Gotcha.
Um,
Yeah.
And-
So
But which means if AV, that would mean AV is equal to V. So if you apply the rotation and it doesn't change it at all, then it has to be rotating around the vector.
or you could have an integer of, or a multiple of 360.
When that would be an identity rotation if it's rotating.
Yeah,
See away.
All right, well, intermission is over. Thank you, Brian, for the lively discussion on eigenvectors. So let's get back underway. Is everyone here? Did we lose anyone? No, I don't think so. So now we're going to talk about principal stresses. So like with the other topics, I'm just going to reach out. Does anyone have a sense of what a principal stress is? It actually has a very, very succinct definition.
It's like the 2 maximums or the 4 maximums.
Yeah, that's way to think about it, for sure. That's a good way to think about it.
It's a stress that's an eigenvector of the tensor.
You're too mathematical. I can't. I think yes. I think the answer to that is yes. That's correct. But the way that I like to define a principal stress is that it's an orientation of the stress tensor at which all of the shear stresses equal 0. That's what an I'm going to be talking about eigenvectors. That's what a principal stress is. So now I've got a cool little GIF that we'll watch for a second. And so we have a figure. I wish they had done a square. It kind of bothers me that they didn't do a square. But we have a rectangle rotating in space. And you can see that we have the normal stresses and the shear stresses. And as they rotate through the medium, these stresses change. The normal stresses and the shear stresses change. And you can see that there's a certain point at which all of the shear stresses right about now equal 0. And in that orientation, you're at a principal stress orientation. And that means that the stress tensor then looks like this. There are 3 normal stresses and 0 shear stresses. This is the principal stress tensor. And then once we have that, so before I click go, what is the relevance of the principal stress tensor? So why is this useful? Can you think about what might be useful about this?
I don't understand why, because not all matrices can be diagonalized. Can all stress tensors be diagonalized, or can only it's because it's symmetric, right?
Well, it is
symmetric, then it has a diagonalization. Is that the rule?
I'm not sure about the linear algebra. My linear algebra skills are less than your linear algebra skills. There's no doubt about that. But I don't know if that's the explanation. But all stress tensors can be diagonalized. Yeah. Yeah.
Would there's no shear stress when it's in that orientation,
Uh-huh.
so that's good.
Yeah, exactly. No, that's a great way to think about it. It's just sort of like handy. It's just useful. It's useful to just think that like the mathematics are way easier if we don't have to worry about 6 of the elements of the tensor. It's just much easier to understand and complicated systems if instead of having, well, essentially 6 elements because it's symmetric, but instead of 6 elements, you have closer to 3.
You can
Well,
also
exactly.
you can separate the variables.
Linear algebra sounds great.
Looks like the system is getting, trying to get to this position kind of, to get to.
It's a more natural, so recall that a rotation of the stress tensor does not correspond to anything physical. It's just our mathematical description. And so the system is not equilibrating to the principal stress directions, but it is a more reasonable way of assigning those coordinate systems. It's just a more reasonable way of, yeah, absolutely. Okay, and then, oh, I clicked the button. So in the Earth, it's a very easy thing to do to assign principal stresses. It's actually quite logical. And in the Earth, we have 3 principal stresses, as we know, because the universe is 3-dimensional. And those 3 principal stresses are the vertical stress, the maximum horizontal stress, and the minimum horizontal stress. And so we'll go into each of those in detail, but just realize that they're physical realities, physical descriptions of what each of those 3 principal stresses are. So first, let's talk about the vertical stress. So say you have your infinitesimal cube, sphere, cylinder, whatever it is, somewhere in the Earth, somewhere deep in the Earth. What do you think is going to be causing? I should back up. Sorry, I apologize. I should back up. So first off, the surface of the Earth. The surface of the Earth is in contact with the atmosphere. What does that mean in terms of the stress tensor? So you have a fluid on top of a solid. When I speak, do you hear any shear waves? Do you hear a compressional wave shortly followed by a shear wave, or do you just hear a compressional wave? You only hear compressional waves in sound. That's because sound propagates through a fluid. And so the Earth's surface is in contact with the fluid, and a fluid cannot support shear stresses. It's just, if you just think about the physics of a shear wave propagating through a fluid, it just doesn't make any sense. And so the Earth's surface has 0 shear stresses on it. What does that mean in terms of principal stresses?
It's oriented.
Exactly. One of the principal stresses is always vertical. Exactly. Yes. One of the principal stresses is always vertical. So now let's go back to what I started saying. which is that you have a cube or an infinitesimal cube, an infinitesimal sphere, an infinitesimal cylinder, or whatever coordinate system you're using, somewhere deep in the earth, and you have a vertical stress. What is that vertical stress? What is causing that vertical stress on that point?
Everything about you.
Exactly. It's the weight. It's just the weight of everything. It's just the earth standing above you, weighing down. And so you can think of that as the gravity pulling all this material down to that point. Mathematically, what this looks like is the integral of the density. So if you have
While you're erasing that, I gotta say, I feel that way about me all the time.
we all do, Brian. We all do. Okay, so you have the density, some function. So this axis is depth. That's a z, I promise. And this axis is density. That's a rho, I promise. And then, so if you imagine density, so what is density? Density is mass divided by volume, right? So if you divide the mass, or
That's kind of all, you know.
yeah, but this isn't going to make sense because of the dimensionality.
Oh.
This isn't going to make sense because of the dimensionality. Anyway, so the weight of the rock is essentially the area under the density of the rock. So if you're at this point right here, the stress acting on you is the integral of, oh, it will make sense. I don't know. I didn't practice this. Sorry. So the point right here is the summation of all of the density above it, right? Because you imagine you have really dense rocks above, that'll increase the stress below. If you have really light rocks above, it'll decrease the stress below. And so the vertical stress is the integral from the surface, which is zero. And in geophysics, I don't know if you guys are aware of this, but in geophysics, we usually say the surface of the earth is zero. And this will say is like 9,000 or something. And so we increase positively downwards. So we start at zero at the surface, and positive direction is downwards. That's just what we usually do. So we take this integral from the surface to the depth of interest. We take the curve, the density curve right here, and we integrate over z, the depth direction. And what we have is the amount of stress when we multiply by g. Oh, I forgot the g. I was gonna say there should be a g. The gravitational acceleration. And that'll give us the vertical stress. And in petrophysical terms, we have something called a density log, where when you drill a well, so you drill a well and you can take measurements in the well with tools, with scientific equipment. And one of the measurements that's commonly taken is the density log, which just gives you an assessment of what the density looks like for different rock formations throughout the column of the earth.
The density measured with gamma rays?
Yeah, I think so. Yeah, I'm not sure. I'm not sure on the petrophysics, but it's there's neutron. No, that's porosity. So no, gamma ray is usually a measure of clay content, or as proxy of clay content. It measures essentially the radioactive decay in the formations. I think the density log does something different. I don't think it's gamma ray related.
No,
It is. Is that?
it's not. So it's a way to like to cross check, let's say. Like it's a different block, totally different.
Okay.
Yeah. Density is the green one.
Yeah, no, they're totally different logs. So you can tell that this is like one section of data, and this is different data. And so this is the density curve. And you can see that like it got to a less dense material, and it got to a higher or more average dense material, higher density material. And so, yeah, the gamma ray is a very common logging metric. But I don't think it's related to the density. It's usually when I see gamma ray, I think of clay content.
Oh, I see.
Yeah.
So that's there should have
Sorry?
other tools for density.
They have, yeah, no,
I
it's
don't-
different.
I can't understand why vertical is always a principal stress. Wouldn't you get that, suppose you have a mountain on one side and then nothing on the other, and so it's heavier on one end than the other, shouldn't that cause a principal stress to not be verticals?
Gravity the best explanation of that?
Well, I mean, it depends. I would say granularity is the best explanation of that. Because if we're talking about like a regional section of the earth, then a mountain is, who cares? It's relative to the aerial extent of that section. A mountain means nothing. And so in that sense, yeah, there's no reason to think it wouldn't be vertical. However, if you go really granular and you're looking directly at a location right next to a mountain, for instance, or maybe a plate boundary where there's a lot of compression, that potentially could rotate the principal stress. But and you're right. I mean, there's always room for error, uncertainty, more exploration. There's always room for that.
But in most of the cases, almost always. the case,
Usually we get away with it. Let's just say we get away with it. Okay. So now I'm a geophysicist and I just showed you a cross section of the earth. I want to talk a little bit about the structure of the earth. I think most of you are engineers, probably haven't had too much exposure to this. So as a geophysicist, I just would like to share it a little bit. So the structure of the earth is split into 4 sections. Potentially, you'll see in a second. So the first section is the crust. The crust is very thin, very thin relative to the rest of the earth, but still it's many tens of kilometers thick. And the crust is actually split into 2 different sections, which is the upper brittle crust and the lower ductile crust. There's a chapter in my dissertation about that. And so that's the first shell of the earth, is the crust. The second shell is the mantle, which is 1,800 miles, I hate miles, that 2,900 kilometers thick. And it composes a system of partially molten rock. It's rock that's under so much pressure and so much temperature that it's partially molten, and it sort of flows around a little bit, and it's this big like shell of the earth, and it's actually where the majority of the mass is contained. The majority of the mass of the earth is contained in the mantle.
Mantle's only partially molten?
Yes. And so then you have the outer core, which is completely molten. This is a liquid. And so actually, if you have an earthquake, a really big earthquake that happens on one part of the earth, and those waves transmit through the earth, on the other side, if the other side of the earth is within what's called the S-wave shadow zone, you don't get any shear waves because they would have had to have propagated through a fluid. And so this fluid system is actually part of the earth. It's big, it's 2250 kilometers. And then you have the inner core, and it's made mostly of nickel and iron. It's mostly nickel and iron, and it's what generates the Earth's magnetic field. It's the Coriolis effect of charged particles falling through the outer core that allows the magnetic field to take effect. And then the inner core is a very dense composite of nickel and iron mostly. There are other elements as well. And this is the center of the earth, very hot, very dense, very high pressure. And so that's the structure of the earth. And then this is not totally germane to a carbon sequestration class, I understand, but I'm a geophysicist and I like to share this. You can think of this as well as a mechanical system and or a chemical system. So the chemical system is what I described, where you have the crust, the mantle, and the core. And the core is, like I said, nickel and iron mostly. And so you can see the inner core and the outer core are the same in the chemical system. In the mechanical system, now we're talking about the strength of the materials, the rheology of the materials. And rheology is a word that just describes the ability to flow. And so you have the lithosphere and the asthenosphere. So the lithosphere is the upper portion of the crust and a little bit of the mantle, and this is what creates the continental plates. The continental plates are a mixture of crust and mantle that is solid enough, not molten, not very molten, and so it allows it to translate across the surface of the earth coherently. And then finally, you have the mesosphere, outer core, and inner core, like we just described. So that is digression number one. There is a digression number two coming up.
Because I got questions. I never thought about it, but it makes sense because in all the ray diagrams, they plot the P, S, and then they put K for the outer core, right? And that's where
Yeah, K is.
You can't transmit S waves, so they.
No, K is a reflection off the outer core.
So you just label it as P to the inner core? Or?
Well, so.
But you call the mantle partially molten because it transmits S waves. Is that right?
It does transmit S waves, and it is. It's like it.
But is its stress tensor necessarily isotropic?
No, I don't think so. I don't think so. I think it's more solid than that. Yeah. Okay, so let's talk about the other two principal stresses in the earth. In the earth, we have SV, the vertical stress, which is like we said, just the weight of the rock falling down. And then we have SH max and SH min. These are the horizontal stresses. Because if you imagine you have three orthogonal axes, and one of those axes is pointed vertically, that means that the other two axes are necessarily in a perpendicular direction, and that would be the horizontal direction. And so we have those two components, the SH max and the SH min. And what they are they're the movements of the plates essentially. They're tectonically driven. If you have a convergent boundary, you have a strong SH max perpendicular to that boundary. If you and of course, because of the orthogonal nature of the axes, you would have the SH min perpendicular or parallel to that boundary. And so these are driven by plate tectonics. So if you have all the plates moving around, and the horizontal forces in the earth are driven by those plate tectonics. And I was going to describe plate tectonics because I'm a geophysicist and I like to share, but I think we don't have time for it, so I'm going to skip it. So we have our stress tensor, our principal stress tensor in the earth. So SV, SH max, and SH min. And you can make the observation that they don't necessarily have to be in that order. You can have SV as the greatest stress, or you could have SH max as the greatest stress. And so this is what's known as Andersonian faulting theory, where if you have systems or like a location in the earth where the horizontal stress is the greatest, or the vertical stress is the least, or the vertical stress is the greatest, you have different systems, there's different relative stress magnitudes that occur. And these relative stress magnitudes give rise to different styles of faulting. So these different styles of faulting are strike slip, reverse, and normal. And usually what happens is that the lowest energy system for a fault to form is 60 degrees from the greatest stress. So if you have a fault, a system here, and a fault needs to form, the lowest energy system for this fault to form is like this, where this angle is 60 degrees. It's an observational phenomenon. I don't believe anyone's done an analytical proof of it. So you may be able to do that. I don't know.
That's weird. I mean, if nobody's been able to do it, I probably can't.
Maybe I'm wrong. Maybe someone has done it. But this is just the lowest energy system for a fault to form. And this is called Andersonian faulting theory, and you can just imagine this as the relative magnitudes of those three principal stresses can be reordered. You can
60 degrees to the vertical from SH.
not necessarily the vertical. So I'm trying to simplify it a little bit because it's different depending on which regime you're in. So if you imagine in the first one, strikes and faulting, SH, the maximum horizontal principal stress is the greatest. That strike slip fault is going to orient with a dip of 90 degrees, so vertically, and at 60 degrees from the SH max. And then if you're where the SV is the least principal stress, that's reverse faulting. And so the maximum is SH max. Again, it'll be at 60 degrees from SH max, but now it's going to have a dip of, I think it's 60 degrees from vertical, or yeah, so the dip of 60 degrees, etc. It's just their preferred sort of low energy states of formation of faults given the stress state, given the relative magnitudes of the stress state.
So
Okay, so are you okay, Brian?
I'm thinking about it. I'm not sure I entirely understand right off the bat, but I've looked at this before. and it's
come to my office.
kinda hard to wrap your head around.
Come to my office sometimes, and sometime we'll talk about it.
Sure.
Yeah, for sure. So now we're going to talk about strain. So the definition of strain is elongation or shortening. That's a very simple thing. You're engineers. I think you've got a pretty good grasp of this. So essentially you have a rod at one length, it's perturbed by a stress, and you get a different length, and that is your strain. And the units of strain are, does anyone know what the units of strain are? What did you say?
Unitless.
Unitless, exactly, yeah. So it's a length divided by a length, so it's unitless. Sometimes when people are trying to, instead of expressing like 0.00001 strain, they say a nanostrain, and they use like nanostrain as a unit. And that just simplifies writing out whatever they have to write out. And so you sometimes see the unit of strain is strain, but it's unitless. And so you can have strain in one dimension, like I showed here. You can have strain in two dimensions, like I showed here. This is deformation occurring in both dimensions. And then you can also have, I couldn't find a good figure, I apologize. But you can see that this figure is, this object is deforming in three-dimensional space, changing its dimensions as it goes, thus straining.
So strain can be represented with a tensor or a matrix.
I don't think so.
Can you have like, there's a twisting component to it, right? You can have rotation of,
I think strain can be represented by a tensor.
I don't think I've ever come across that.
You have plane strain, you have plane stress model,
Right.
which would necessarily imply that it's tensor bonding.
I thought both of those were the stress tensor. I don't know.
so there's,
I'll go to Master Chat GPT.
maybe strain is a vector, perhaps. If there's no twisting component, then it's a vector, right? And then in which case you would get a matrix that converts stress to strain and similar to Hooke's law. Because you'll have a strain in at least three components. You have strain in X, strain in Y, strain in Z, right?
Right.
And then you'll have shear, and you should have an amount of shear as well.
Well, there's no shear stress.
I don't think-
Straight.
Well, I don't think so. I think we're a little more general than that, but I think I actually don't think you can have shear straight. Can't you? I don't know.
I mean,
Yeah, if you have the change in X with respect to L, then you have the change in respect with respect to the other direction, right? I mean, I could try on the part of.
No,
You can have shear strain theoretically, but in the earth, if we are oriented with the
If-
principal stresses, we have no shear.
Yeah,
That's a
if
good
your stress is diagonal.
I don't know. The answer is I don't know if there's a strain tensor. I should have researched that before I started this. I don't know the answer. I don't know if there's a strain tensor or not. I don't know. I don't know. It might be a vector, it might be a tensor, it might be, it's not a scalar. You're right. It's definitely not a scalar. Oh, what just happened? Oh, yep. Strain is a tensor. Similar to stress, strain describes how a material deforms under stress. It is a measure of deformation representing the displacement between particles in the material body relative to a reference length. Strain is mathematically represented as a second-order tensor, which allows it to account for both the magnitude and direction of deformation, including changes in volume, which is dilation, and shape, which is distortion. Thank you, Brian.
If Sam Altman is correct anyway.
If who?
Sam Altman, the CEO.
Oh, gotcha. Gotcha. We need to share my screen now.
Yeah, I'll stop sharing mine.
Is that right, Brian? Yeah, okay.
That's good.
Yeah, so strain is a tensor. I'm glad I learned something great today. That's awesome. And so tracks, let's take a second. All right. So strain is a tensor. It describes deformation, dilation, and deformation. And in the lab, we can cause stresses and we can cause strains. And one way in which we do that, and there are several, is to look at a triaxial system. So this is what's called a triaxial apparatus. What you do is you put a rock sample, or it could be a metal sample or a cement sample. It doesn't have to be rock, but geomechanics, so usually a rock. You put it here and you apply a force, a load on it from some kind of hydraulic system up top. And that causes stresses and strains in this sample. And so if you were to take data from the laboratory, and many people do every day, what you see is a curve like this. So on this axis, you have strain, and on this axis, you have stress. And here, there's a little section before you start with a linear elastic system. You start with cracks are closing. So you imagine your rock sample, maybe it was at a 1,000,000 degree or 1,000,000 feet of depth. You brought it up to the surface. It expanded a little bit from that journey. And so it's got cracks in it. It's got impurities and imperfections. And so what happens when you first start loading it is those cracks begin to close and you get a nonlinear relation between stress and strain. Then what happens is you have a portion of time over which the relation between the strain that you observe, and this is axial stress and strain. Usually we consider this axial stress and strain. This linear portion is elastic. So you push on the rock and you get the same amount of strain and stress out of it. Or for the same amount of strain, you get the same proportional amount of stress. And then you get to this point where you have plastic deformation taking place. You not only are creating deformation where if you were to stop the deformation, you would just recover the system. You actually start permanently altering that system.
So elastic is necessarily not strain. Is that right? That's why it curves down.
Elastic is
Or
definitely
sorry,
not.
plastic is not a strain. It's
No, plastic is definitely strain.
it's at a strain if it doesn't create force, it doesn't impact forces on.
So the definition of elastic is that it's recoverable. So if you think about like a spring, if you push on the spring, there's strain, but if you take the force away, it returns. The definition of plastic is that it's not recoverable. So if you take like putty and push on the putty, it doesn't recover when you take your fingers away.
Right. So plastic deformation reduces the strain.
Plastic deformation.
Or
That might be dependent on the rock. I think usually in these curves, I see that it dips down so that the trend causes the stress, the strain. I see the stress relaxed essentially. Basically, the plastic deformation causes a relaxation of the stress. Because and you can think about that if you put that force on that putty, kind of just sort of like absorbs some of the force, right?
Yeah, that makes sense.
There is more strain response to less strain.
But it at a constant strain, if it moves moves to reduce it, but you're assuming a constant strain, right? You're assuming a fixed strain, and so if it moves for plastic deformation, you'll just end up putting more force on it till you get the strain. at
But it's
the
both
level.
elastic and plastic. It's not an egg. It's not a binary.
I feel like you need to look at my rock mechanics textbook.
Yeah, rock mechanics.
Okay, I have one last thing to show. We're gonna skip the final section. Maybe do it. Oh.
That's pattern like, does apply for all types of rock or?
That's an interesting question. This is very generalized. This is very just sort of broad stroke generalization. There are likely species of rocks out there that defy this. And exactly where, how, and what way, I'm not familiar with, but I'm sure there are species out there. Yeah. And then the last thing we'll go over today is a concept called hysteresis. And this is the concept by which if you load a sample, even if you're still in the elastic portion, where theoretically you should get that recoverable deformation, you load the sample, you take one path through the stress strain curve. And when you unload the sample, take that pressure away, you get a different path through that sample. It's kind of like I always joke with myself that when I take one route to campus and another route home, that's hysteresis.
And this happens even if you're in the without plastic deformation.
Yes, even in the linear elastic regime, we oftentimes see this.
Weird.
So we did talk about hysteresis in the class a bit with respect to relative permeability, because as CO2 and water both migrate through a medium, if it is imbibition or first entering, it will be different than as it's draining because of capillarity and irreducible saturation CO2.
Absolutely.
So it's
the same thing, but mechanics instead of fluid flow.
Is this something that happens when you do it just quickly, or is it something that happens even when you unload it very slow?
Even slowly, I'd imagine. Yeah. Okay. Well, I will see you guys in 2 days. And we'll do another session. It'll be a little different because there will be some of my own research in there, and I think it's sort of more hands-on real world in that sense.
Thanks for teaching.
Yeah, no worries. Yeah. So thank you all very much.
Well, one last question. Why do we get hysteresis?
Sorry?
What's the reason for hysteresis in these?
My understanding is it's like grains sliding. So if you imagine you have two grains like this and you load them, even though they're elastically deforming, they can still move relative to each other. And so that means that when you take away the load, the strain is different. I think it's due to deformation in the.
So can you repeat this experiment on the same material and keep getting hysteresis every time? Or the next time you do it, does it?
I mean, it would be asymptotic, of course, right? It wouldn't just be like suddenly you stop getting hysteresis. You slowly decrease the amount of hysteresis.
Do it.
But
Yeah,
I'd imagine. So basically, what you're talking about is doing this to a rock 1 billion times and seeing if you get completely elastic behavior. That's just philosophical. That's philosophy. I'm not a philosopher.
Well, I know with metals. In metals you bend it and then it gets stiffer.
Yeah,
right?
That's strain hardening. Yeah,
Strength hardening. So maybe that's kind of similar to.
I'd imagine. Yeah.
All right.
Yeah. Thank you, everyone.
Thank you.